What's truly remarkable about conic sections is that there are so many different ways to define them. In the previous video, we took a cone and a plane and sliced the cone using the plane. Using the slices, we got all different conic sections. In this video, we'll consider distances. Let's first look at a circle. So this is a circle. We have a fixed point and a fixed distance. This is the moving point. This point is always at a fixed distance from this point. The locus of this point is called a circle. So let's write that down. A circle is the locus of a point that is always at the same distance from a fixed point. So this is how we define the circle in terms of distances. This fixed point is called the center of the circle. Let's move to the next one. This one is called the parabola. We have the focus, that's the fixed point, and we have the directrix, that's the fixed line. Now when we move this point P on this parabola, it will always be at the same distance from this fixed point as it is from this fixed line. Now remember, measuring the distance of a point and a line, we always take the perpendicular distance. Let's see this in action. Let's see when we move this point, it's always at a fixed distance from this point F and this line directrix. So let's play the animation. This is what we have. So when we move this point on the parabola, the distance from the focus and the perpendicular distance from the line remains the same. This circle denotes that. These two distances are always the radii of this circle. All right, so let's define the parabola. The definition of parabola using distances is this. It's the locus of a point that is equidistant from a fixed point and a fixed line. This fixed point is called the focus and the fixed line is called the directrix. Let's look at the other two, the ellipse and the hyperbola. So this is called an ellipse. We form this using these two fixed points. They're called the foci. And what we do is we let this point move, but the condition is that the sum of distances from these two fixed points always remain constant. This distance is the radius of this circle and this distance is the radius of this circle. So when you see the animation, see that the sum of the radii of both of these circles remain constant. When one increases, the other one decreases. The increase in radius of this circle is met by the decrease in radius of this other circle. Let's see this in action. Okay. When the point moves, the sum of distances from these two fixed points, the foci, remains constant. If one circle increases in size, the other one decreases. The increase in radius of one is equal to the decrease in radius of the other. So this is called an ellipse. Let's define ellipse. It's the locus of a point, the sum of whose distances from two fixed points is always constant. These two fixed points are called foci. So this is an ellipse. Let's move to the hyperbola. For this hyperbola, we again have two fixed points. They're also called foci. And in this case, the difference of the distances remain constant. Again, the magnitude of the difference of distances remain constant. If this distance is greater than this distance, we subtract this from this. Basically, we subtract the smaller one from the larger one. Now, if the difference of distances remain constant, this means the increase in radius of this circle is same as the increase in radius of this circle. Let's see this in action. Let's move this point. The increase in radius of both the circles will remain the same. This means the difference of radii of both the circles will always be a constant. When that happens, we get the hyperbola. So let's define the hyperbola. Is the locus of a point, the difference of whose distances from two fixed points is always constant. These two fixed points are called the foci. Now there's again another interesting way to define these conic sections in terms of the ratio of distances from a fixed point and a fixed line. This is called the concept of eccentricity. The way we define eccentricity is it's the ratio of the distance from a fixed point and the distance from a fixed line. So the numerator is the distance from this point and the denominator is the distance from this line. Right now the eccentricity is 0, which means the distance from this point is exactly 0, which means we're sitting on this point. Let's play this animation and see when this eccentricity increases, what happens to our conic sections. So let's play this. Okay. So our eccentricity is now increasing it's moving from 0. Now what you might see looks like a circle, but it's not a circle. Let it grow a little bigger. Okay, so what we see is actually an ellipse. For an ellipse, the eccentricity is always less than 1, which means we're always more close to this point than this line. So this is the eccentricity for an ellipse. It's moving more and more close to 1. Okay, so this is opening up. Let's see what happens when this is exactly equal to 1. Okay. All right. So when this is exactly equal to 1, this ellipse finally opens up, and what we get is called the parabola. Recall that the definition of the parabola is it's the locus of a point that moves in such a way that the distance from this fixed point is exactly equal to the distance from this line. When the distances are equal, the ratio will be exactly equal to 1. And that's why we're seeing a parabola. But what happens when the eccentricity increases from 1? Let's play this. Okay, let's increase the eccentricity. So now this is opening up. It still looks like a parabola, but it's not a parabola. When eccentricity is more than 1, what we actually have is the hyperbola. So for the hyperbola, the eccentricity is always greater than 1. For parabola is exactly equal to 1. For ellipse, it's between 0 and 1. So again, another way to define conic sections using the concept of eccentricity. So let's write that down. First, let's define eccentricity. It's the ratio of the distance from a fixed point and the distance from a fixed line. This is called the focus, and this is called the directrix. When the eccentricity is between 0 and 1, we get the ellipse. When it's exactly equal to 1, we get the parabola. And when it's more than 1, we get the hyperbola. Now you might be wondering, where's the circle? Now, when eccentricity is exactly equal to 0, we got a point. So this is called a point. Now some might say that this is a circle, but it's not a circle. Technically, this is a point. But we still say that the eccentricity is 0 for circle. And the way we do this is by assuming that the directrix, this line, is at infinity. Imagine that this line is very far away from this point. And the distance that we have from this point is fixed. So we're moving in a circle. For this circle, the distance from this point is something finite, but the distance from this line, which is very, very far away, is infinite. If the denominator is infinite, the eccentricity is equal to 0. And the farther this line is, the better our limit is. At infinity, this is exactly equal to 0. So eccentricity is 0 for a circle, assuming that the directrix is at infinity. It's 0 for a point. It's equal to 1 for a parabola. It's between 0 and 1 for ellipse, and it's more than 1 for the hyperbola.